Great. Thank you for having me. My name's Kieran. Please excuse my very gravelly voice today. I am in day one of a cold and I'm on like my seventh cup of ginger tea. But yeah, I'm very happy to be here. Yeah, I'm talking about the same stuff as Jakob did. And in particular, I'm going to talk about how we prove this breaking of translation variance when n is large. And in particular, when the parameters p can be anything you like, and then also n can be not an integer. And so the technique is coming straight from this paper by Dominic Capin, Peled, Samatij, and Spinker. So everything that is in this talk is the technique is lifted from there. Okay. So let me start with some definitions. So, as Jakob started, we start with Z2 and its dual. Okay, and I'm going to let L be the graph with vertex set given by edges of Z2, which is essentially the same as the edges of the dual, because every edges goes over exactly one edge of the dual. Okay, and then edge is given by joining E and E prime. These are now edges of Z, yeah, Z or Z2 or Z2 dual. If and only if E and E prime share a vertex and a face. Okay, so here's a nice picture. On the left we have the two in red. I haven't drawn any edges just so everything's a bit clearer. Z2 dual in blue, and then here is the lattice L. Okay. So yeah, as I said, note each vertex of L is in projection with exactly one primal and one dual edge. Okay, one of these is north oriented, and the other is west oriented. Depends where you're on the lattice as to which one is which. Okay, and then I'm gonna define our mirror configurations, which you know very well now. So, but I'm going to define it on a slightly more general graph than before. So just let D be some subgraph of L, and then a mirror configuration is a map omega from the vertices of D into empty or N or W. That's a mirror. I'm going to call that a mirror configuration. Okay, where N means we choose the north pointing edge that is associated to that vertex, W the west one, okay? And we're going to write omega D for this set of configs. Okay, and as before, each configuration gives us a model of loops where the loops just bounce off our mirrors, etc. Okay, please excuse the wonky drawing. Okay, so now we can define our measure, which Jakob defined it only on torus, but I'm going to define it on this general N, general subgraph D. So So let P be the this vector of P's where these guys are all, I'm going to just write P star for each of them, is all positive, and the sum of them is equal to 1. Okay? And let n be greater than 0. And D is subgraph L. And in particular, I'm going to say, well, I want to have quite general boundary conditions. So let psi be a mirror configuration on the entire lattice. Okay, and then for omega, also on the entire lattice, which coincides with psi outside of our D, so on vertices of L, take away the vertices of D, and I'm going to say on the boundary of D, so the vertices on the boundary, let P, and then our boundary condition is psi, we have P, N, and D. Omega is exactly what we expect it to be, so I have my normalization constant, which will depend on all the same things, and then Pn, so the number of north mirrors in omega, Pw to the number of west mirrors in omega, empty to the number of uh, empty vertices in omega, and then n to the number of loops, where this time we have the number of loops which intersect which are on the edges of D. So LD of omega is the number of loops of D. Okay, so this gives us more general boundary conditions than what we had before, and we're going to consider really specific types of domains, in particular something like this, so which I'm going to call a primal domain. So another definition. But these are primal domain if it's going to be a union of the faces of the primal graph. Okay. And we're going to add the simply connected. So no holes in them. Okay. So here's an example in the drawing. Jakob had a black and white coloring for his faces of L. And here I've added that in. One of them's red and one of them's not colored. And we just taken the union of those ones which are red. Okay. Or you can think about it as just a union of faces of Z2. Okay. We're going to say the boundary of D gamma, we're going to call that a primal circuit. This is just a loop in the primal graph. Okay. So this is all great. Same definition holds for dual. And we will identify just D with the subgraph of L. Just to be very precise there. Okay. So now I'm going to define a specific kind of boundary conditions. Above we had very general. So if D is primal domain, let P, I'm just going to write 1 in the superscript, be exactly this P psi and D when psi is equal to omega, well, I'm going to write superscript brackets in 1, okay? Where omega 1 is the configuration on the entire lattice such that it's always the primal edge. Omega 1 of V is primal for all of V, okay? And then similarly, we can do the same thing for dual. Okay, so we define, we're just going to write P2, P, and D. So these are the measures that we're going to consider. Here's an example. Here's my gamma, and outside of it, I've just only got primal edges. Okay, and we'll need a useful domain Markov property, which is that, well, you can probably already see it, which is that the measure inside of this gamma really doesn't care about what happens outside of gamma, because if I draw some loops on here, then they're never going to escape gamma. Okay, so what we want to say is that if D is a primal domain and psi is in omega L such that psi is primal on gamma, which is the boundary of our domain, then, well, this measure is the same as the one we had up the top. Okay, and then a similar holds for dual. All right, this is proof by picture again. It's that, well, you have an exact bijection just by don't do anything to the mirrors, and then because the loops cannot escape this gamma, the weight of each configuration is the same. Okay, and we'll use this a lot. Okay, so now I can state my theorem. So I'm going to state two theorems. One is a simpler one, and I'm hopefully going to try and prove the simpler one for you today. So let D be primal domain, and E be some edge inside. This is an edge of L inside D, and P as above. Then there exists some constant C, depending on P, greater than 0, such that for all n bigger than 0, and here n doesn't have to be an integer again. So we have the probability that E is on a loop of length k. This is going to be less than C of P n to the minus 12 k. Okay, nice. So what does this say? It says that the loop lengths decay exponentially, so long as this thing is less than 1. Okay, and well, C of P is fixed, and so long as n is large enough, we can just take it large enough so that n to the 1 over 12 is n to the minus 1 over 12 is cancels this out to be so that this is less than 1. Okay, nice. So this I want to prove to you later on, but I can state theorem 2 first, which is the following, and which is much stronger. So we say that there exists some n naught depending on P greater than 0, such that n greater than n naught, the following holds. So let dk be an increasing sequence of primal domains such that they become L, so their union is L. And then we have the convergence of these measures, P and dk, weakly to some measure, which I'm going to just write as P1, P, and L, where P1, P, and L is some infinite volume Gibbs measure, which is one, no, I don't, that's sorry, which is supported on configurations with no infinite loops. Okay, and further, we have that P1 on all of L and P2 on all of L are distinct. Okay, so this is really nice, and it's a bit stronger than what we had before, not only in the sense that the parameters range is larger, but also that we actually have convergence to an infinite volume measure. Okay, nice. So as I say, I'm going to try and prove theorem one, which is just saying that we have exponentially decaying loop lengths through through a given edge. Yeah, and if I have time, I'll say a few words about the last one, about theorem two. And I should note here that this C of P, this doesn't depend on D. This is independent of the domain. Okay, cool. So proof theorem one, I'm going to need some more definitions. So first of all, some gamma, which is the primal circuit, we're going to say is a primal circuit in omega. Well, if all omega is if omega is primal on all of gamma. Okay, so really if the edges of gamma appear in omega. Okay. Okay, so now fix some omega primal circuit in some gamma a primal circuit in omega. Okay. And then we're going to say sigma is a primal garden in omega inside gamma if well, it's just a sub-circuit. Primal, okay, contained in gamma. Okay, such that they don't intersect. So gamma intersect sigma is empty. Okay. This word garden is coming from the paper of Dimmock et al. We just thought it'd be nice to continue using the notation. And then we say sigma is a primal cluster of omega in gamma if, well, it's a garden or primal garden which is not inside any other garden. Which is either primal or dual. Okay, so here's a nice picture. Here's my gamma around the edge in red. And then I have some mirror configuration inside. And well, okay, so here is a garden. It's a uh, sub circuit. And it doesn't touch the edge, whereas this one does touch the edge, so it's not a garden. Okay. And then this one is also a garden, and so is this one, but only the outer one is a cluster because it's maximal. Okay, so this guy and this guy are clusters. This guy is a garden but not a cluster, and this guy is neither a garden nor a cluster. Okay. So how is this proof going to work? So it's going to come in three parts. So first is the idea of what the authors of that paper call a repair map. So what's this going to do? It's going to fix some gamma as we have, and it's going to say, well, fix all the primal clusters, and then we're going to, that's number one, and then we're going to shift the dual clusters just slightly up and to the right, or up and to the left, doesn't matter, such that they become primal, okay? And then three, we're going to fill the rest of the space, so the space not inside any cluster, with trivial primal loops. That means put mirrors like everywhere so that, like this, so that they're the smallest mirrors possible and so that they're all primal. Okay? Okay. So this is going to allow us to prove that the probability that the space outside of the clusters is small. In particular, the probability that it's bigger equal k, this is going to be less equal some constant, again, n to the minus 12 to the k. Okay, nice. And then that is going to give us what we want, right? Because a long loop, well, if you, let's say, imagine I have some long loop, then there is going to be some smallest circuit or garden which surrounds that loop. And in particular, the long loop is going to be contained, it's not going to be contained in the clusters inside that loop, okay? It's going to be in the space outside the clusters. So the probability of a long loop is going to be less equal probability lot of space outside the clusters in sigma L. Okay? In particular, maybe I'll draw a picture. Like if I have a loop here, then this is the smallest circuit containing it. Or if it's here, it'll be in here, and it's in particular contained in what is not the clusters. Okay, so let's make this rigorous. Okay, so I'm gonna do another definition. So just let E1 of omega gamma be the edges in L in primal clusters. Okay, E2 of omega gamma is similar. That's the dual ones. Let V1 of omega gamma be the vertices in L. I'm going to say strictly in primal clusters and V2 similar. Okay, here's a nice drawing. On the left, we've got E1s, it's the edges of L, which are contained in the primal clusters. And here's V2, the vertices strictly in dual clusters. And now the space outside the clusters is what we're interested in. So let's define E out of gamma omega to be just the edges inside domain, inside gamma, take away E1 union E2. Okay, so that's what this looks like in this setup. Okay, so now I can define my key proposition, which is this second step here. So the space outside the cluster is being enlarged, we want that to be small. So the probability, here I'm going to drop my notation before. I'm just going to write P, but it's the same as we had before. So probability of E out omega gamma being greater or equal K is at most C of P n to the minus 12 to the K. Okay. So we're going to have to actually slightly edit this proposition for a reason which I'll now explain, which is that we want this set E out, which is the things not in any cluster, to have two properties. Firstly, we want it to be connected. Why? Because that means that then we're going to have to be counting the number of sets of size K inside gamma, which could realize this E out. Okay, and we want this number to be at most some constant, the power K. And this connectedness gives us that. Okay, well, and we can actually check that as we've defined it, it is connected. So let me just do another definition, which is the boundary edges in gamma, which is just edges of L instance the gamma inside gamma, and here's a nice drawing of that. Okay, and well, we have that this thing is actually contained in our E out as we've defined it, right? Because we defined clusters to be not things which touch the boundary. Okay, so this definitely has all of the boundary edges in it, and well, maybe we need to modify our definition of connectedness slightly for these ones, but that's fine. Okay, so great. But we also want our E out to have a second condition, which is the following. We want there to be no trivial loops in E out. Okay, now this is a bit more subtle. So why is this? Well, this means that when we apply our repair map, which is this map I defined up here, where I fix all the primal clusters, I shift all the dual clusters, and I fill all the remaining space, which is E out essentially, with these trivial loops. Well, that means that we're going to gain a bit of probability for every single edge in E. Let me be a bit more clear about that. Well, if this is true, there's no trivial loops. That means that every loop in this E out is of length at least 6, okay? Which means that there's at most 1/6 of the size of E out loops, which are in there, and we get like an n to the 1/6 E out at best. However, when we apply the repair map, we're going to get trivial loops everywhere, so that means loops of length 4 exactly, which gives n to the 1/4 E out. Okay, and this is strictly larger than our 1/6 E out, and that's where we're gonna win. Okay, and the eagle-eyed of you may observe that the 1/6 minus the 1/4 is going to give us exactly this 1/12 here. Okay, so we need to just check that E out does contain no trivial loops, and well, it doesn't, but it might. So if so there are no trivial loops which are really in the bulk of of the interior of gamma, which are containing E out. Why? Because, well, if I had one here, there's one. Well, then it's a cluster, or maybe it's containing a larger cluster. But happy days, it's definitely in a cluster, so it's not in E out. It's not in the space around clusters. However, as we've defined it, things on the boundary are not clusters. Okay, so there might be these little ones on the boundary. So we're just going to define our way out of that and say, well, E out is the edges in gamma, take away E1 union E2 union these trivial loops on the boundary. Okay, so now here's a better picture of what we should look like. This is our E out, and here's an example of one in the boundary. Happy days. Okay, but then last thing is that this might destroy our connectedness, right? Because our connectedness came from the fact that the boundary is all contained in E out, but okay, now we need to change our proposition. So here's the full version of the proposition. It says let gamma be a primal circuit and for all P, there exists C of P greater than 0, such that for all N bigger than 0, and for all K bigger than 6, the probability that, well, we're going to just add this condition in that we want, that the boundary really is contained in E out. And the E out is greater or equal K in size, is less equal C of P, n to the minus 12, the K. Okay, this condition here is now, this is the same thing as there's no boundary trivial loops. Okay. So let's try and prove this proposition. So with definition, if A is some subset of L, or the edges of L, let A and then this arrow be just A translated by, I think the right thing is just -1/, root 2, 1 over root 2. So we're just shifting it up and to the left by 1 step. Okay, this is going to turn every primal thing into a dual and vice versa. Okay, and here's the repair map, which I promised right at the start. Okay, so again, I have some fixed gamma that I'm doing this in reference to. And it says R of some configuration is equal to, well, I'm going to keep, as I said, keep everything the same on primal clusters. This is the vertices strictly inside primal clusters. And then I'm going to take everything inside dual clusters and shift it. That's my shift arrow. And then outside of all that, I'm going to just put, well, just primal mirrors everywhere. Okay, so this omega 1 is that configuration with primal mirrors everywhere. And that's going to be on the rest of the things, which I'm going to call V out star omega gamma, and I'll define that properly just now. So we already had E out. What's V out is equal to, well, it's V of the vertices in the domain, take away V1 union V2, okay? Omitting the omega gammas. And then my V out star is V of the take away, this time V1 union V2, where we shift it. Okay, so here's a nice picture. Here's V out. Everything that's just not in a cluster or like on the edge of a cluster. So this one is fine. And then V out star is the same, but we've shifted our dual clusters up and to the left by 1. Okay, great. Little note. Size of V out and V out star is the same. Okay. Okay. So let's prove the proposition. So this comes in 3 parts. We're going to show that we're going to fix some set, which is going to be our E out. So everything which is not in a cluster. And we're going to show that for omega with this given out, we have that the probability of R of omega over the probability of omega is greater or equal than sum f of p n to the 12 to the size of this E out. Okay. Then if we let omega out comma E be, this is configurations such that E out omega gamma is equal to our E. So if all of the omegas was give this fixed E out, then we can bound the probability of omega out E. And we'll get this is less equal, be 3 to the 1/2 mod E, and then again f of p n to the 1/2 n to the 12th again to the minus E. And that's great. So in particular, this is small, again, when n is large. This is some fixed thing, this is some fixed thing depending on p, only dependent on the lattice and not on the domain. Okay, and then the last step will be to sum over the possibilities for E which realize this E out. Okay, so let's do the first bit. So what's the ratio of these two things? Well, here I've just literally written out the definition of our measure, and I've written it so that here we have a product over all vertices, and then Pn, and then like an indicator that the R omega has a north mirror at that vertex. Okay, and then same for west, same for empty. For each vertex, one of these will be realized. And then I got my n to the number of loops. Okay, now, and here's the key thing which we used, which is why we set this all up, really, which is that if here's my omega and here's my R of omega, shifted my dual cluster and I've filled in everything with primal mirrors outside of the clusters, then the domain marker property, like whatever happens in here is independent from what's going on here. And in particular, it's preserved by this map. Everything's going on here is the same as what's going on here. And also here and here. Okay? So for every vertex in V1 and also in V2, these things here are going to cancel. Okay, and so what's going to be left is what's going on outside. So here I'm going to just like copy this for speed's sake. Okay, and here I'm going to say, well, this is actually just V in V out star, and this is V in V out, and then the same thing. And then what's going on over here? Well, how many loops are there in, well, again, and yeah, the number of loops in here are the same as the number of loops in here, so that cancels, and the same here and here. So how many loops are there in here? Okay, well, we already did this. It's every loop is of length 4, so it's n to the 1/4 mod E out. And we know that all the loops in here are of length at least 6. So we can say this is greater or equal n to the 1/6 mod E out. Okay, but now we're almost home and dry because we can rewrite these factors on the left as just take the smallest of the p's and the largest of the p's to the size of V out. And then we have an n to the 12, which is coming from the subtraction there, mod E out. Okay, and then I'll use the fact that the size of V out is less equal a half of the size of E out. So this gives us, this is greater or equal P min over P max to the 1/2, n to the 1/12 to the size of E out. Okay, and that's part 1. So we showed that the ratio of these two is bigger than some constant depending on P times n to the 12 mod E out. Okay, and then I'm just going to try and at least do this part. So we want to try and get a bound on the probability of this omega E out, the probability of the E out is realized as E. Okay, and this uses a very simple lemma, which is that if T goes from some set E to some other set F, and the probability of E, which is an element of big E, is less than or equal to constant times its image, probability of its image, where here A is large, and T inverse of F is at most some constant Q, then we have probability, a bound on the probability of E, okay, which is going to be less equal Q times the probability of F. Okay, this is probably very easy to see, and I think I'll just skip the details. Okay. So this map T is really our map R, and it's increasing the probability for each configuration. Why? Because it's putting in loads more loops in these trivial loops. So that's why this A is large. Okay, but then we need to bound how the entropy of this map, like what's the number of things which can be sent to the same thing. Okay, so R is sent from omega out, goes from omega out E to the image of it under this R. And well, we want to ask how many inverses does some omega prime have under this map? And well, how many choices are there? Well, the information we lose when we do R is when we put all those primal mirrors in, because for each one we put in, there's three choices of what it could have been. Could have been a primal or dual or no mirror. So this is at most 3 to the size of V out. Okay, and this is at most 3 to the 1/2 E by the same bound we have. Okay, so that's this bit here, and we already did this bit, right? This is the probability of R of omega over probability of omega greater or equal this thing we had before. So we have the probability of E in this case, which is omega out E, is less equal 3 to the 1/2 P max over P min, also to the 1/2 n to the -1 12th to the size of E. Okay, and that's what we wanted to prove. Yeah, is what we wanted to prove. Okay. Okay, and then part 3 is to just show the probability is to finish the proof. So the probability that, well, recall we had this is contained in E out, and the size of E out is greater or equal K, less than or equal to some constant n to the -12 to the K. And this is done by just take the left-hand side, do a union bound over all possible E's that could realize the set E out. And then we have some, we apply this, and then we have to count the number of possibilities of E and what of a given size. And well, that's given by this connectedness that we had before, which is coming from this condition here. So we'll have an extra some constant of the K going into here. Okay. So I'm essentially out of time, but here's our theorem that I wanted to prove, which is that E is on a loop of length K. We want it to be bounded by something small to the K. And what we've done so far is said that, well, everything which is not in a cluster inside our gamma, the size of that being a greater or equal K is small in K. And so what we do is, so we fix a loop of length K, we find the smallest circuit around it, and that becomes our gamma. Okay, and now inside that gamma, we have this, we certainly have this estimate, because our long loop must be contained not in clusters, it must be contained in E out. And then we have to sum over all the possibilities of that circuit which surrounds our loop, and then over all possible loops of a given length. Okay, And in both cases, we have the same thing of them, the number of these things being some constant to the k. Okay, so again, we just end up with a slightly different constant here. So long as n is large enough, this thing will be less than 1 and we have this exponential decay. Okay, I think I'm going to leave it there. Thanks very much.